In this video, we are going to find the median of two sorted arrays. This is Leetcode problem number 4, and it's a Leetcode hard problem, and it has been asked in Google, Amazon, Apple, Microsoft, and many more interviews. So let's see the problem statement. So it says that you are given two arrays and these are sorted. So you can see in the input 2, 4, 9, 10, 16, this is sorted similarly, and nums2 is also sorted. And you have to find the median, combined median of these two arrays. So first of all, let's understand what is a median. So a median is a number which divides a list of numbers into two equal parts. So let's say we have 1, 2, 3, 4. So in this case, if you draw a line between 2 and 3, so we can assign a value, let's say the average of these two, 2.5. So if you assume 2.5 is here, then 2.5 is bigger than 2 elements and it's also smaller than 2 elements. So it's dividing the array equally. In this case, there were even number of elements. So the median, that is 2.5, was not belonging to the set. But let's say we have, instead of even number, we have odd number of elements. So let's say we have 1, 2, 3, 4 and 5. So now you have to find what is the number which divides this group of numbers into two separate groups. So in this case, 3 is the median because there are two numbers which are less than 3, two numbers which are more than 3. So it's dividing the array equally. Now this was the case for a single array. Now we have two arrays and we have to return just one median. In this case, it's 12. So what you do, you would say that it's already sorted. So in sorted array, it's very easy. If you have a sorted array, you can simply go to the midpoint, and that element will be the median. If it's odd, if it's even, then you pick two middle elements and take the average. So it's a O of 1 operation in case of sorted arrays. If it's not sorted, it will take O of n times since you have to scan the whole array. But in the case of two arrays, you don't know, you even don't know which array the median will belong to. It may be in the first element, first array, it may be in the second array, or it may not be in any of these arrays if the number of combined sum of these elements is even. So it's a bit tricky here. So first of all, if you don't know the optimized solution, you can always say that since these two arrays are sorted, we can use some concept similar to merge sort. That is, we put two pointers. Either you first merge them and then take the middle element, or you can just keep a counter that here 2 is the smallest element. So you know that here number of elements is 1, 2, 3, 4, 5. 5 elements are here. Here we have 2, 4, 6 elements. So you know that there are 11 elements. So 5 elements will be on the left of median. There will be one median element in this, and then 5 on the right of this. So you have to find which element comes 6th in this array. So you can keep two pointers, one here and one in the other one. Whichever is smaller, increment the counter 1. Then you move this pointer here, 4 and 8. Again 4 is smaller. So you move the pointer here. Now 8 and 9, 8 is smaller, so you move this pointer. So till now we have scanned 3 elements. Then 10 and 12, 10 is smaller, so increment this one, 4. And then 10 and 12, again 10 is smaller. And then 16 and 12, 12 is smaller. So you move this pointer here. But in the counter, you see that the value of counter is now 6. So 12 was the 6th element and you return the median. So this approach will take O of n plus m time, or divided by 2, because we will only scan till half, and where m and n are the size of first and second arrays. So m is the size of this one and n is the size of second array. And we can do it without any extra space, that is just two pointers. So space will be O of 1. but we can do better. This is the brute force approach. We are just scanning both the arrays. So we have to use the fact that these are individually sorted, and we will use that fact and try to reduce the time complexity. So let's see how we can use the fact that these are sorted. So in the case of single list, what we were doing, we were trying to find a partition which divided it into two halves. All the elements in the left half were smaller than the median. That is, all the elements in the left half were smaller than all the elements in the right half. In the case of two arrays also, we have to pick all the elements of these two and move them in two separate partitions, such that all the elements in the left partition is smaller than all the elements in the right partition. So this is what is the goal. So let's see. So and also all the elements in both the partitions should be same. So if we have 10 elements here, there should be 10 elements in the other partition also. So we have to find such partition. So it may not be that always possible that we find a partition in the middle of both those arrays. So if you divide both the arrays into half and half, then this array had m elements and this had n elements. So the left part will have m by 2, right part will have m by 2. Similarly here it will be n by 2. So combined sum of this left part will be m plus n by 2, and so will be the sum of right part. But this may not be the case always, and we may have to shift this partition in both the arrays. So let's see. So this middle partition would be the simplest and ideal case, but let's say these elements were a bit smaller on average than the elements in the nums2, then maybe we may need to shift the partition a bit to the right. So if we shift this partition by one right, then the number of elements in the left partition will increase by 1. So we have to move this partition one left by the same amount. So if we divide in the middle exactly, then clearly this is sorted in ascending order. So these elements will be less than these right half elements, and these elements will be less than the right elements in the first array. So if we move this partition in the first array to the right, we have to move the partition in the second array to the left, so that number of elements in both the partition remains same. So our goal is that we keep all the elements to the left of partition in first array and left of partition in the second array in one partition, and all the elements in the right partition of first array and second array in the second partition. So this is the goal. Only thing is that we need to find the place where those arrays should be partitioned. So let's say we partition this array here, let's say at 12 after 10, and in the second array we keep it after. So let's see the number of elements here. M is 2, 4, 5, n is 6. So there are 11 elements. So number of elements in each partition should be 5 plus 6 by 2, that is 11 by 2, that is 5. 5 elements should be in each partition. So here we have already picked 4, and one of the partitions will have one more elements. So in this case we will keep one extra partition in the left. If this is odd number of elements, so we will have one extra element in the left partition, and the right partition will have one less. In that case, this element will be the median. The highest value, the max value in the left partition will be the median. If these are even, then both the partition will have equal elements, and we will pick the max in the left partition and min in the right partition and take the average. So these are the only two cases. So in this case it's even, so we will keep one extra element in the left. You can also keep the other way, you can keep the extra element in the right partition. In that case the final median will be the minimum of elements in the right partition. So in this explanation I will be sticking to the first case, that is we will keep an extra element in the left partition itself. So instead of 5 we will keep 6. So we can add 1 here in the formula. So m plus n plus 1 by 2. So this will take care of both the cases. Let's say we have 10 elements. Then we will have 10 plus 1, that is 11 by 2, that is 5 in each partition. If we have 11 elements, then it will be 12 by 2, 11 plus 1 by 2, then 6. So this formula takes care of both the cases. So in our code we will be using this formula to find the number of elements in partition, m plus n plus 1 by 2 in the left partition. So we have to keep 6 elements in first and 5 in the second. So if we partition it here, so I am not arriving at the final solution, but let's say the partition is here after 10. So we have already 4 elements here. We need 2 more. So in the second array, the partition will be here. So 2, 4, 9, 10 will come, and 8 and 12. These will come in the left partition, and the other elements 16, 19, 20, 22, 28. These will come in the second partition. In this case, I have taken the solution only, but let's say this was not the case. So we don't know where the partition would be put. That is what we have to find. I am repeating again and again. So let's say the partition was here, 2 elements. Then we need 4 elements here. So the partition would be 2, 4, 8, 12, 19, 20. And in the right we will have 9, 10, 16, 22, 28. But is this partition okay? No, because we see that elements in the left partition 20, 19, these are more than some elements in the right partition. So the maximum in the, let's say, second array, whatever is the second array, the maximum here or maximum among these should be less than minimum among these elements. So here the maximum is 20. So 20 is coming from this array. So clearly we need to move this partition to the left. So let's try here 19, and so this will move right to keep the number of elements constant. So if in the second array we move the partition left, it should move right by same amount. So now let's try the new values and check whether it works or not. So I'm doing a brute force now, then we will arrive at optimal solution. So now 3 elements here, so 3 elements here, but 19 is again less than 10. So again we need to move this left. So let's move it here, and then this one will move by the same amount. Now we see that it's correct. We have 2, 4, 9, 10, 8 and 12 which are less than all the elements in the right partition 19, 20, 22, 28. But if we move it by one step at a time, again the time complexity will be of the order of m, the minimum among these, but that is equivalent to in a way m plus n. So this does not improve the solution by much. Now we will use the fact that these are sorted. So instead of moving by one step, we can use some sort of binary search approach. So first we can take the partition in the middle. So we have 3 elements and the other will be 6 minus 3, that is 3. So we have these 2 partitions. Now the maximum here in the first array should be less than minimum in the right of, it's already less than all the elements in the right, so no need to compare here, and no need to compare in the left part since these belong to the same group. So only thing that needs comparison is that max in the left partition of first array should be less than or equal to min in the right partition of second array. So this is one condition, and also we need to compare that the maximum here in the second array in the left of partition should be less than minimum of right partition of first array. We don't need to compare with right partition of the second array itself, since all the elements are already sorted and all the elements here are more. Similarly, we don't need to compare with the left partition of first array, since these belong to the same partition. So the other condition is that max of left partition of second array should be less than equal to min of right partition of first array. So these two are the condition. If these two are satisfied, then this partition is correct. In this case, it's not correct, since 19 is not less than 10. So now we need to shift the partition. How we will do that? So we will follow the binary search approach. So first we pick the middle element, and that's coming from the binary search way of doing things. So we know that if let's take a generic case. So this is the partition in first array, that is P1 elements on the left of this, and P2 is the partition in second array, that is P2 elements in the right of it. And we know that max L1 is more than, so let me draw it again. So this is P1, number of elements in first array, and this is P2, that means P2 elements are here, and max of left partition of first array is more than min of right partition of second array. So minimum element is here in the second array, this one, the immediate next element to the P2, and max element here is P1 minus 1th element here. So this is more than this element. So this white one is more than this yellow one. We need to move this partition left, because this should not be more. So the partition is too much right in the first array. So in A1 we need to move the partition to the left. Similarly, in the second array we need to move the partition to the right. So in this case, this was the left pointer, so we were comparing with the middle element. So again, we can use the binary search way of doing things. We keep two pointers, left and right. So left was equal to 0 and right was equal to m. M is the size of first array. Now we will move this right pointer to one left of P1. So now in this case, if this is the case, then we will make right equal to P1 minus 1, because P1 cannot be in the partition, because if it's in the partition, then again it will be more than this. So our solution will be to the left of P1. So that's why right is moving. There may be other condition of violation, that this element here, this is the maximum among left partition of second array, and here it's the minimum in the first array. So there may be case that this is more than this. So what is this case? It's max of L2 is more than min of R1. In this case, this partition is too much left. So we have to move the left to the one right of P1 by the same logic. So in this case, we have to change L equal to P1 plus 1. And if the condition is satisfied, this condition, these two, then the partition is correct. We just need to find this max among this left partition, combined left, and min among the combined right, and take the average, or just the maximum among the left partition, depending on whether the total number of elements is even or odd. Also, there are a few edge cases which we will see once we start writing the code, or let's see it straight away. Let's take this case. So in this case, let's take the partition. M is 4, N is 2, 4, 6. So total number of elements is m plus n is equal to 10 even. So initially p1 will be here, 2 elements, and p2 will be here, 3 elements, because this will make 5 elements. So number of elements in the partition will be m plus n plus 1 by 2, that is 11 by 2, that is 5. So now we compare this max here with min here. It's fine. So max L2, 2 denotes the second array, L denotes the left partition of second array, is less than min of R1, that is 30. So this is fine. Now the second condition was max of L1, that is 25. 25 should be less than equal to max here, min here, sorry, min R2, that was 8. But 25 is not less than 8. So this condition is violated. That means this P1 is too much to the right. So we have to move P1 left. So now in this case, let me erase it. So here L was initially 0, R was 4, and middle was 2. P1 denotes partition 1, number of elements here. P1 was 2. So this partition is too much to the right since it was more. So we will make R equal to P1 minus 1, that is 1. So now L is 0, R is 1. So the middle will be 0 plus 1 by 2, that is 0. So partition comes here, just one step. This is a small example, so it's shifting by 1. If it's a big array, it will shift by half of this left part. So now again, here the partition will be shifted to the right. So now we have minimum here is 22 and maximum here is 10. Again the condition is violated, that means this is too much to the right. So shift the partition left again. So now R will become, so now L is 0, R was 1. So now R will become P1 minus 1. So P1 was 1, 1 minus 1, that is 0. So both L is 0, R is 0. So partition 1 will be 0. So there will be no element to the left of partition. So all elements will be in the second partition. So this is a edge case. So in this case, what is, so here P1 is empty. P1 L is empty. P1 R contains all the elements. That is 22, 25, 30, 34. And here the number of elements will be 5. That is 2, 4, 6, 10. And 8. So and in the right there will be just one element, 15. So this maximum here is 10, which is less than minimum here. This is fine. But for comparing this, there is no element in the left part of this. So what should we compare? What is less than 15? So in this case, we will, this is the edge case where there is no element in the left of any of these arrays partition. So we will make it minus infinity, negative of infinity. In code it will correspond to int min. Similarly, there may be case where all the elements in any of these arrays come in left partition. There will be no element in the right partition. What we need to make this comparison. So in that case we will have plus infinity or int max in that case. Now I think we have covered all the cases. Let's start writing the code. So first m is nums1 dot size. Similarly n is nums2 dot size. So before writing the code, let's also analyze the time complexity here. We have two arrays, first length is m, second is n. Let's say we always find partition in the smaller array. You can also do it in the bigger array, but it is wise to do binary search on a smaller, since binary search takes log of n times. So if n is smaller, it will be better for us, because once we find partition is in one of the arrays, we know the number of elements in one of the arrays, we can straight away know what should be in the left partition of the other array, because we know that number of partition in each array should be m plus n plus 1 by 2. So we can subtract p1 to find p2. Similarly, if we know p2, we can find p1 by the same formula. So it's better to do it in a smaller array. So we find partition in a smaller array, the middle point, and then reject one of the parts. And depending on whether this was less than this value or this was more than this value, or we will either change the left pointer or right pointer. So left will come here if that is the case, or right will come here. So we will reduce the size of this smaller array by half and again do the binary search. So it will take log of m time, where m is the smaller of this. So we can write log of min of m and n. So if the first array is smaller, we will continue. If the first array is larger, we will call the same function with numbers reversed. So instead of a1, a2, we will call the same function with a2, a1. So that way the first element will first array will always be smaller or equal. Now let's write the code. So we will compare that if m is more than n, then we will call the same function find median sorted arrays with nums 2, nums 1. Else, if this is not the case, we will continue our logic. So we will have L equal to 0, R equal to M, and we will continue our search till L becomes more than right, left becomes more than right. And also this returns a double. It returns because we may have to take the average of two middle elements. In that case, it will be a double value. If m plus n is odd, then it can return int, but that is not always the case. So while L is less than n, we find the partition 1. Partition 1 equal to L plus R divided by 2. And similarly, once we find this, P2 is simple. Number of elements in each partition is m plus n plus 1 divided by 2. So this is the number of elements in each partition. But P1, we already know number of elements in the left partition from first array. So we have to subtract it here so that we can add the remaining elements. So if you add P1 and P2, it should add up to this half of the number of elements, combined number of elements. So P2 plus P1 is this, P1 will get cancelled and it will remain. So these are the initial partitions. Now we have to check our condition that max in the left partition of first array should be less than min in the right partition of second array. So for that, let's first find the max. So we will write max L1 is equal to, so remember that there was a edge case where there were no elements in the left partition. In that case, it will be minus infinity. So if P1 is equal to 0, in that case it will be int min, else it will be nums P1 minus 1. Similarly, we are finding min in the right of first array. So again, the same edge case, that there is no element in the right partition of first array. In that case, P1 will be equal to m. So we have to take int max, else nums it should be nums1 first array, nums1 p1. Similarly, the same thing for second array. So left of second array, right of second array, p2 p2, and this would be nums2 nums2, this would be p2 p2. Now we have the value, so we can check the condition. If max L1 is less than equal to min of R2, this is the first condition, and max of L2 is less than equal to min of R1, then we have found the partition is correct. Found partition. So in this case again there are two cases if the number of elements were odd or even. So if m plus n modulo 2 is 0, in that case we have to take the two middle elements, that will be max of max 1 max L1 and max of L2 plus min of min R1 and min R2 divided by 2. But we have to return a double, so in case of 0.5 it will get lost if we do integer division. So you can do either divide by 2.0 or you can explicitly cast it to a double. But if the number of elements is not even, then we have to just return the max. In the left partition. Now if this was the case for correct partition, if that is not the case, then it may be violated due to one of these conditions failing. So the first way of failing would be that max of L1 is more than min of R2, and there will be one more condition, else that will be max of L2 is more than min of R1. So no need to write the condition since that is the only case left. So if max of left of first partition is more than min of right of second partition, then that means partition in the first array is too much to the right, so we have to shift it left. So in that case we will change the right pointer to point to p1 minus 1, and in the final case the other case is that the partition in the first array was too much to the left. In that case we will move the left partition to the right of p1, and that's it. Let's see if it works or not. So there is some typo here, so we missed the if case. So else if, so there is some error. Let's see. So I looked at it, and one of the errors I can see is that I forgot to change this n. So let's see if it fixes the problem. Yeah, it does solve the problem. So at least it passes for this case. Now let's submit if there are any failures. And it passes. So all the test cases are accepted. So this solution seems to be okay. And you know the time complexity is O of minimum of log m. So m is the minimum of the two arrays, so that is the time complexity. So if you don't understand it, you can try to see the video again. So the main concept here was that we are looking for optimum partition in one of the arrays. If you know the partition in one array, you know the partition in second array. Since it should be divided equally, so we know the elements in each partition. So if the crux of the problem is that if the maximum in the left of first array is more than this minimum in the right partition of second array, that means this partition is too much to the right. So we have to do a binary search in left part. In the other case, if the maximum in the left of second array is more than minimum in the right partition of first array, then that partition in the first array is too much to the right, too much to the left, we have to move right. So this is the only concept here, and every time we are ignoring half of the array, so that's why it's taking log of m time.